Recording.
Okay, so in this portion, this lecture, I want to talk about finding arc length, yet another application of integration, finding the arc length of a curve. The curves we're going to be talking about are functions. So go back to your definition of functions, and they pass the vertical line test. So that's it's maybe a subtle information right now because basically everything we've been working with have been functions, but it's important, as you will see later on in chapter 10 in your next quarter's class 1C, that you can find arc length of parameterized curves, which are not necessarily functions. So just know that here what we're talking about is finding arc length of a function y equal to f of x. And arc length, I don't know if that language makes sense to you, but it's just this length of the arc. So if this is f of x from A to B, you're finding the length of this. Like if you had a measuring tape that was like maybe one of those cloth measuring tapes and just put it on here and then calculate the size of this, that would be what your arc length would be. So the length of the arc. You did that in trig. In trig, if you guys remember, you talked about how to find this arc length of say a circle of radius r, angle theta radians. And if you remember, you said that the arc length is equal to r theta. So the concept of arc length has been introduced to you guys earlier, but here we're doing it a little bit less regular shapes than a circle, and basically just functions, any functions. We want to find the arc length of it. When I say any functions, we're talking about continuous differentiable functions and from point A to point B on x values. Of course, the independent variable could be s, it could be t, it could be x in this case. We try to stay away from s because s is actually what we call the arc length function, so that you'll see in a little bit. But I guess you could call it any independent variable that you want. In this case, it's x, y. Okay, so the way it works is basically the same thing you did before. You're still going to partition, and like this will be x0, this will be x1, this will be x2, and so forth. And each of these points or variables, a values, would correspond to a point on the curve. And I'm not going to draw all of them. Well, actually, it doesn't make a difference. Let's just. I have a partition size 5, but it need not be the case. Of course, we're going to take the limit as n goes to infinity, so that's not going to be the case. And then, so this point would be x0, f of x0. This one would be x1, f of x1, and so on and so forth. x2, f of x2, x3, f of x3, and so forth and so forth. Now, if I just exaggerate my curve, and let me just put it some, and these will be my points, and there's parts of the curve, right? And suppose this is xi, f of xi, and this will be xi plus 1, f of xi plus 1. And you want to find the arc length. What we do is we're going to connect these dots with straight lines, and then calculate the total length of that. And then we take the limit as n goes to infinity of the partition size. Sorry, limit as n goes to infinity for the sum of those lengths. So first thing I have to do is I have to figure out what is that length. And that length is really the distance formula. So if I call it Li, which is the length of the line segment that connects these two, Li would be square root of xi plus 1 minus xi squared plus fxi plus 1 minus fxi squared. Now, this part is fine. But for this one, we actually can use what we refer to in Math 1A as mean value theorem. Just a reminder. Again, it's a technical step here, but it's needed. It's necessary. The final point of this whole derivation is just a formula, which we're going to use in calculating the length of a curves. But I still have to walk you through the derivation of the formula. So if you remember, mean value theorem was that if I have, and again, the drawing that I'm having here is it's not the same as the drawing we're having here. It's just some other drawing for the purpose of mean value theorem. So if I have a function f of x and I have 2 points, suppose this is a, this is b, and of course this is f of x. The mean value theorem says that there is some c where f prime of c, the instantaneous rate of change or slope of the tangent line, whichever you want to call it, is equal to the f of b minus f of a over b minus a. This is the average rate of change. This is the slope of the secant line, right? F of b minus a over b minus a. This is instantaneous rate of change. This is the value of the slope of the tangent line. So what mean value theorem says, at some point in between a and b, upon the condition of differentiability of the function on that interval, at some point the slope of the tangent line matches the slope of the secant line. That's what mean value theorem. So now again, the geometry of that is not important in what I'm going to do here. What's important here is that I can replace this, which is like this, f of b minus f of a, f of b minus f of a. I can replace it with f prime of c, b minus a. So I can replace f of b minus f of a with f prime of some c times b minus a. So your b is x plus xi plus 1 and a is xi. So Li, with this understanding now, not lithium, Li is equal to square root of xi plus 1 minus xi squared plus f prime of, let's just call it xi star for some c in between, for some xi star in between, times again xi plus 1 minus xi, and then the quantity of this squared, which is nice because now I have, this is delta x squared, this is f prime of xi star squared delta x squared. So it's going to be square root of 1 plus f of xi star squared delta x. And that's basically the heart of the formula. So the length of each of those curves is going, or each of those straight lines is going to be this. The actual length of the curve is approximated by adding all of those together, approximated by adding all of those lengths. And then the exact value of it, if the limit exists, is going to be the limit as n goes to infinity of that. So if I just write out what I just said, arc length is approximately sum I equal to 1 to n. And the way I have written is probably 0 to n minus 1, doesn't matter. Of sum 1 plus fxi square prime square. Sorry, is there? Yeah. Please note the change. I put a prime here and here. This is supposed to be a prime. I just forgot the prime. Delta x, and then arc length is exactly limit as n goes to infinity of this sum and this is the definition of integral. That's the integral from a to b of square root of 1 plus f prime of x square dx. And that's really the formula you need to remember. The derivation was just to show to justify the formula, but really the formula is what you need to remember. The appearance and usage of mean value theorem is not, if you don't remember it, it shouldn't really make you feel like, well, no, I don't understand this. It's a good reminder. I think it's a very, very important theorem to remember. You'll see it in other places as well. But if you don't remember, it doesn't mean you're not going to understand the formula. It's still the formula is, it's a standalone by itself. Once the derivation is through, the formula is what you need for your calculations. Let's go ahead and do a couple problems. Let's do number 9 from the homework, which basically just uses this formula. So number 9 from 8.1 gives you a function y equal to 1 plus 6x to the 3/2. And then gives you x bounds from 0 to 1. I'll just go through the process. I find y prime, which is 6 times 3/2 x to the 3/2 minus 1. Yeah, you can do that at your rate, at your speed. So in this case, it's going to be 9x to the 1/2. Y prime squared, remember there's a square there, right? Y prime squared is going to be 81x. So the integral is going to be integral from 0, arc length is going to be integral from 0 to 1 of square root of 1 plus 81x dx. Depends how comfortable you are with your integration by now, but if you still want to do u sub, you can another u sub here. U is equal to 1 plus 81x. I can see students doing it without doing the introducing a u, although you're still doing the substitution. Du is equal to 81 dx. 1 over 81 du is equal to dx. So it's going to be integral 1 over 81 u to the 1/2 du. And then when x is 0, u is 1. When x is 1, u is 82. So it's going to be 1 over 81, 2/3 u to the 3/2 from 1 to 82. Which is going to be 2 over 243. 82 to the power of 3/2 minus 1. They want to leave your answer in the exact form, and that will be exact form of it. Okay. Let's do number 17, because number 17 has a trick inside. So I think it's a fun one. It's actually 17 is a very fun example. 17. So again, be patient with yourself, but it's going to be a fun one. Y is equal to 1/4 x squared plus 1/2 ln of x. And then the x bounds are between 1 and 2. Let's just go through the process. Y prime would be 1/2 x plus 1 over 2x if I take the derivative. Y prime squared, now this is an interesting one, is going to be 1/2 x plus 1 over 2x squared, which is 1/4 x squared plus twice of the first times the second. So it's going to be 1/2 plus 1/4 x squared. Sorry, there's a minus here. I copied down wrong. And I know this is wrong because I know what's going to happen and it's not happening. So more or less, it's an advantage to having done a problem a million times. Okay. And then y prime, and this is a catch really, 1 plus 1, because it's y prime squared plus 1. Y prime squared plus 1 is going to be equal to 1/4 x squared minus 1/2 plus 1 over 4x squared plus 1. That's a plus 1. And then 1 minus 1/2 gives you 1/2, 1/4 x squared plus 1 over 4x squared plus 1/2. So the good thing about this is that's really, and you can verify, is 1/2 x plus 1 over 2x squared. So how this was a minus and you had a negative 1/2, now plus of it gives you positive 1/2. Now, how would you know that? Well, it's just the expanded form of that binomial. And that's how you get the exact form. So the arc length will be integral from 1 to 2 of square root of this quantity squared. Sorry. Yeah, And the good thing is that the square and square root cancel out, positive values. So, and then antiderivative of that would be and then you plug it in. 4 over 4 is 1, plus 1/2 ln of 2, minus 1/4, and minus 1/2 ln of 1, which is 0. So you get 3/4 plus 1/2 ln of 2. One of the tricky ones. It's not terribly tricky, but it's nice. 12 is something like this too. So if you want to more practice, do number 12. I leave it to for you guys to do it. But that's a nice one. Okay. 12 is now, well, okay. Let's do number 13 because 13 has a different flavor as 17 and 11 and there's other 9 and those other ones. Because let me show you what 13 is. And maybe you can tell the difference. As soon as I write it, you see the big difference because 13 now is x is a function of y, not y is a function of x. It's like a different flavor there. Okay, do the same thing though. So your formula would be integral of square root of 1 plus f prime of y squared dy. So let's just switch it. That's it. That's the only thing. As I told you guys, the independent variable doesn't matter. Whatever it does, as long as you have a function, independent variable doesn't make a difference. Makes no difference. So, okay, now dx dy, if I take that, I'm going to emphasize this dx dy, so I put it in that form, is 1/3 derivative of first times the second, first times derivative of second. 1/3 is for both of them, that's why I wrote it. So I get 1/6 y minus 3 over root y plus 1/3 root y. Sorry, my writing is not very clear here. Let's take a common denominator here. Multiply that by 3. But no, it already has everything it needs. Never mind, sorry. And then the next one I multiply by 2 root y times root y. Notice it only had 3. I need 6 root y, so I need a 2 root y, and then it already has a root y. Okay. As you would expect, now I'm going to square it, add 1 to it, and then take the square root of it. So arc length is going to be integral from 1 to 9 of square that. Get a common denominator. And then this is again like the situation we had before. Now we have 4y plus y squared minus 2y plus 1. Yeah, I guess you guys see the light at the end of the tunnel here. Y squared plus 2y plus 1 is y plus 1 squared. comes out as a square root of that. Because it's between 1 and 9, it's positive. I don't need to put any absolute value. It looks kind of scary, but it's not actually. If you've done, feel comfortable about last chapter, especially the first discussion of integration, this should be coming more comfortable for you. So it is 1 to 9 of y over 2 root y plus 1 over 2 root y. 1 to 9 of root y over 2 plus 1 over 2 y to the negative 1/2. I'm going to use a power also. So I get 2/3 times 1/2 y to the 3/2 plus 1/2 times negative 2 y to the 1/2 1 to 9. Just a basic calculations now. 2's cancel out, you get 1/3 y to the 3/2 minus y to the 1/2 1 to 9. Square root of 9 is 3 cube is 27 divided by 3 is 9. 1 is 1/3. So remember, arc length has to always be positive because it's the length. Length has to always be positive. So one sign that you know maybe you did something wrong. Again, if you get a positive number, it doesn't mean you did everything correctly. So you have to make sure you check everything, you check the work, and go back and look back through it. But if you do get a negative, for sure you did something wrong. And then go back and check your work and see what you did wrong. It could be as simple as like maybe you wrote when you subtracted, you did something wrong, or calculation part, maybe you made some mistakes. But or it could be as serious as maybe you made some conceptual error, or you set up the formula incorrectly and you got the negative answer. So, or you found the antiderivative wrong. Any of those. Okay. In this section, there's a discussion of what we call the arc length function. It's not, or it doesn't feel or seem useful right now. You may feel like, well, why do I need to know this? What am I going to use this for? But later on, like in chapter 10, you guys are going to parameterize using arc length function, arc length parametrization. And then in chapter 13, it comes in when you're talking about curvature and such. And then, of course, in math 1D also it comes up. So although it seems right now like why we need it, but it is one of those things that's going to come up later. And instead of introducing to you guys then and then having to refer back to this section as where it comes from, they just bring it up here, explain it, and then later on you at least have heard it and seen it and just use it for other purposes. So I guess that makes a little bit more sense in author's point of view to do it this way. So what's the arc length function? It literally is a function that you define to calculate the length of a curve from some fixed point to some variable. So it's arc length function. It says S of x is equal to integral from a to x of f of t f prime of t squared dt. That's basically it. There's really nothing more than this. Basically, it says if I have a curve, whether my curve is f of x, then the integral from a, this is when t is equal to a, and x equal to a. But you cannot use x because, as I said, x is being used as upper bound. So let's just call this f of t. But so the length of the curve from t to some x, that length is your from some t to x, that length of that curve is going to be your value of your function. Your as I said, f-axis will not be necessarily here. But let me get it. Okay, and it's always positive, of course. Okay, as long as your x is bigger than your a. Now, the important one is the SDX. It will be ddx of a to x of square root of 1 plus f prime of t. Yeah, you get the point, right? Because this is now fundamental theorem calculus part 1 that we talked about. So you just get 1 plus f prime of x squared. So you have a nice derivative for your arc length function as well. Okay. There are some questions in the homework that says use Simpson's rule and calculate the arc length, so you're kind of approximating. Once you have an integral, then your Simpson's rule becomes an option if you cannot find the exact value. But yeah, just try those. Try those, see if it makes sense. Otherwise, don't worry too much about. You need to know that you can apply Simpson's rule to integrals, definite integrals. But what example am I going to use, or what type of question I'm going to use to see if you know how to use Simpson's rule? It really depends on what other questions I put on the test. But you will be required or expected to know how to apply Simpson's rule to different integrals. But as I say, I need to still figure out when I look at the rest of the questions in the test, which of those questions will be a better fit for checking your understanding of Simpson's rule or trapezoidal rule, again, whichever. Okay, so do know it, but I'm not sure if I'm going to use it for arc length per se. So we'll see. Okay, I hope this was helpful. I showed you guys some example of it, and I went through the revision and then show you some examples. I talked about our arc length function. If there are any questions, again, let me know, and I will do solutions for it. If you guys don't ask me questions, it's hard for me to make it. So problem session video, because I believe I do enough, not enough, but some problems during the lectures. So unless I know what other type of questions you need, it's hard for me to make a video related to a particular topic beyond what I already provide. So please feel free to tell me what questions you want me. It could be homework problem, it could be any problem from the section. And if there's a special concepts that you're still struggling with, let me know. Maybe I can make another video for that. But other than that, I hope this video was helpful, and I hope to hear from you guys about your concerns or difficulties you may be having. Okay. Yeah. All right. Thank you.